Hi everyone, my name is Andrew Trask. Thank you so much for being here, and today I'm going to be giving a talk called Remote Data Science. And remote data science really starts with a key problem, which is that our ability to answer important questions in society is limited because we can't access existing data, meaning that there's data that already exists that's in another country or another organization or perhaps another department at the organization you're in. And if you had access to this data, you could solve an important challenge, but just because you can't access this existing resource, you are limited in your ability to answer important questions. Okay, in this talk, we're going to ask this question: is it possible to answer questions using data we cannot see, the data that is in these other locations? Now, before we jump in, I want to walk through a handful of use cases. So just to give a little bit of a sense of what these scenarios tend to be like. So the first one we're talking about is global trade. So here's a couple of actual statistics from Canada and the United States. So Canada records the sum total number of goods that are leaving Canada and headed to the United States, and inversely, the United States records the amount of goods that come from Canada, right? And then they publish these statistics on a monthly scale, as we see here. So these are actual numbers from February of 2021. But perhaps surprisingly, sometimes these statistics don't line up, meaning that the amount of, say, straw in February that Canada thought they were exporting to the United States doesn't match the amount of straw that the United States thought they were importing from Canada. And inversely, sometimes goods that supposedly were coming from Canada, either Canada didn't know about or came from some other location. And this brings us back to our key premise, right? That our ability to answer important questions like where are goods flowing from, where are imports and exports going and coming from, is limited because we can't access existing data, right? Because that data is somewhere else. In this particular case, the United States can't access most of the world's data about its imports, about the stuff that's being imported into the United States, because that data is stored in other countries. Inversely, Canada can't access most of the world's data about its exports because that data is stored in other countries. Once those goods leave Canada, that the ledgers, the databases, sort of the tracking resources are stored in other places. And so, if you actually look at kind of this perspective on global trade and where goods and services are flowing to, we actually have maybe just a somewhat limited view of what's going on. Each country has a high amount of information about what's going on in their own borders, but once stuff leaves their jurisdiction, there's no central database that just tells everyone where everything is, right? Because each country has sort of a different slice in terms of what's going on. And you might ask, why is this important? Well, it's important for a wide variety of reasons. Tariffs and taxes, tariffs and taxes, sanctions and foreign policy, economic surveillance being a handful of these types of things. But let's ask this bigger question. Like, why can't we track global trade together? Why can't allies such as the United States and Canada know what's going across their borders between the two of them? And the big reason here, one of the reasons, is that the world's national trade statistics organizations can't put all their data into one place, right? Because that would be a bit of a strategic mistake, right? It puts any given country a little bit too much at risk to give a copy of that low-level information to another country, even if they are really close allies. And this brings us back to our key problem, right? That our ability to answer important questions is limited because we can't access existing data. In this case, even very close allies don't necessarily know and can't get to the bottom of what these trade discrepancies are really all about. Okay, so let's talk about another use case, right? Which is breast cancer. So, breast cancer is treatable when it's caught early, but unfortunately, hundreds of thousands of people still die from it each year. Unfortunately, it's so common that it affects around 1 in 8 women at some point in their life. And an underlying issue here, if detecting it early is so important, is that actually we still make quite a few mistakes in our detection process, meaning that the detecting it is actually quite difficult. It's not uncommon for there to be a 1 in 4 false positive or negative rate in a breast cancer screening program. And AI machine learning models, even ones deployed into production, like this statistic here, deployed into production in early 2021, had around a 1 in 3 false positive and false negative rate. And the question that I ask, is like, okay, wait, if AI machine learning is supposed to be so good, and really this is like a simple image classification or relatively straightforward image classification problem, like why is AI machine learning not doing so well? But if you take a closer look, what we'll actually see is that there's very little data available, right? In the sense that there is this huge amount of resource of labeled data that exists. We're generating around 800 million images per year, and this has been going back 10, 20, 30 years. But if you took all the world's known research data sets and combined them together, this would still account for less than 0.1% of the data that has been produced. And you can sum this up with kind of a simple phrase, which is that each medical institution that tries to do AI machine learning is only really training on data that they collected themselves, despite the fact that huge amounts of information exists around the world. And so if you're training on 1 to 2 million images for an incredibly fine-grained, detail-oriented classification issue, it's no surprise that our AI classifiers aren't doing particularly well when identifying pictures of animals in ImageNet required orders of magnitude more training data to be able to do. But perhaps more optimistically, this leads us to sort of a different conclusion, which is that breast cancer classification, at least as a machine learning task, is not necessarily a technology problem, right? It's a partnership problem, right? AI is not predicting mammograms reliably because no one can sort of create that 100+ globally distributed data sharing partnerships needed to get a sufficiently large, diverse training data set. Or put another way, the world's hospitals can't put all their medical data into one place to train a breast cancer AI, right? And then this again brings us back to our key problem. Our ability to answer important questions like, what does breast cancer look like, is limited because we can't access existing data. All right, let's keep talking. Hopefully we start to see a pattern between these things, right? So let's consider money laundering. So United Nations Office on Drugs and Crime estimates that around $1.6 trillion in criminal proceeds are laundered annually, and the way money laundering works is relatively simple, right? So if I've illegally gotten some financial revenue and I need to move that into my main bank account so that I can then spend it, what I do is I push it through other small businesses somewhere else. And then I bounce that money around from bank to 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 bank, so that then when it finally gets deposited in Pablo Escobar's Citibank account, right? Citi's like, we don't know where this money came from. It just came from that other bank, right? And so when we ask why it's difficult to detect money laundering, right? To detect that this money originally came from sort of an illicit activity or illicit location, it's because the world's bank that it was being shuffled around from can't put all their ledger data into one place so that they can just follow the money, right? It's not even necessarily a complicated analytic to the extent that we're just talking about sort of money moving through enough places that can't pool their ledger information, right? So just to be very specific, say a bank like Citi can't access most of the world's data about where its money comes from because that data is stored in other banks, right? Brings us back to that key problem. Our ability to answer important questions is limited because we can't access existing data. And this specific use case has already been picked up in the context of privacy-enhanced technology. So, the Financial Crimes Enforcement Network in the United States, the FCA here in the UK, and most recently the US-UK Prize Challenge, which also has a theme based on financial crime. And so again, I hope you're starting to see this theme, right? That there are lots of important problems that could be solved if we were able to work with data that's distributed across many different organizations. Now, the last one here I want to talk about is algorithm accountability, right? And this is the notion that algorithms are increasingly driving important decisions in society, and they're often proprietary and they're often operating over private data. This makes it really difficult for us to understand, in the first instance, whether any particular algorithm is biased in any sort of unfavorable way. But even more challenging is that the impact of algorithms on society is often collective. So for example, if you went into a city and you wanted to find a job, and there was a host of different algorithms at lots of different employers, they were all making different types of recommendations based on who should see your resume. No one algorithm is necessarily controlling your outcome. It's actually the collective, the collective nudging and recommending and actions of all these different algorithms together that are affecting your outcome as a citizen. Right? So you have another issue where this notion of why can't we study the collective harms of algorithms is because the world's organizations can't all put all their algorithms and their predictions into one place for study. It's distributed across lots of different businesses sort of around the world. So again, we have this key problem. Right? Our ability to answer important questions in society is limited because we can't access existing data. I mean, there is data, the solution does exist, but it's just an access problem. We've walked through a handful of different use cases. We could keep going on these. There's really quite a few that fit this type of template. This template of we could solve sort of X important challenges in existing data, but no one can access any data but their own. And it's really based on this one core assumption that in order to do a data science project, you have to put all the data into one big massive database. And you go around to a bunch of different businesses or government departments or whatever and say, hey, can I have a copy of that, right? Can I have a copy of that data set because I'm doing this project? And what we're going to be talking about today is the creation of federated data networks, right? And federated data networks are sort of the inverse of this, where instead of asking for a copy, you simply send your analysis around to lots of different institutions and sort of remotely control this. Okay, so how can we solve this issue, right? Well, privacy-enhancing technologies is certainly going to play a role. I imagine if you've been around the space, you might have heard some of these phrases, things like homomorphic encryption or federated learning or secure multi-party computation. And if you've been around pets for a while, you'll know that they've sort of been grouped into different use cases into different value propositions, really. So input privacy and output privacy being perhaps the most talked about, but then we also have different verification techniques that can provide different types of guarantees. But what I'd like to argue is that these are actually just components, right? These are just sort of subsystems to one higher level ability. Pets are going to make it possible to answer questions using data owned by somebody else, right? That really all these individual algorithms and individual pieces, of course, they play vital roles and they're very important, but they are sort of the trees, and the forest is this broader ability. And so what I want to talk to you about today is really what the implication of this end-to-end ability is like, and then sort of give us a bit of a sense for how these different components actually play into this larger ability, right? So by analogy, if you're looking at an individual component like homomorphic encryption or secure multi-party computation or federated learning, right? These are like car parts. They're like, pistons or a steering wheel or a drive shaft or whatever the case might be. But in society, we don't necessarily yet have a car, right? And by a car, what I mean is like this very relatively simple to use, accessible to the everyday person, technology that you can just kind of get in and drive somewhere, right? You don't have to worry about your piston design and whether you configure this, that, and the other in just the right way and building some custom bespoke, piece of infrastructure for every single use case you want to do, right? You don't have to change your car really based on what destination you're going to, unless you happen to be, maybe you put on snow tires or something like this, right? But your car is sort of the same based on no matter what you're doing. And I also want to sort of mention that in a sense that because we don't just have this general purpose vehicle, it's also really difficult to understand how sort of what the more emergent behaviors are going to be. So let's dive into this. Okay, so what is the car of pets? I'd like to argue that the car of pets is called a domain server. A domain server, right? And by analogy, it's like an Apache web server for private data, right? So an Apache web server is this big collection of individual technologies for distributed computing and threading and cryptography that where you can put some text files into it and it enables someone somewhere else to download those text files into their browser in a way that they can then be rendered, right? So it's sort of a file hosting a server. Now, a domain server is going to act a little bit differently because whereas a Apache web server is more built around this idea of sort of data that you want to make public in a really scalable way, the domain servers are actually about keeping data private while making it possible for other people to use that data to answer specific questions. Let me show you what I mean. So let's say I'm a data owner, okay? And I've got a server that I control, right? So my own cloud infrastructure or my own on-prem server stack, whatever the case might be, right? And so I launch a domain server inside of my compute infrastructure, right? And I load in some of my own private data as the data owner, right? Medical images or personal data, whatever the case might be. And then I create an account for a data scientist, right? Username, password, and most importantly, in orange here, I set question limitations, right? And what I'm specifying there is I'm saying, hey, my data is in this server, and for this particular person, I want to limit what types of questions that person is allowed to use my data to answer, right? Like I might want to allow this person to answer the question, what causes cancer, without being able to answer the question, does any particular patient have cancer, right? So different types of questions. Some questions are okay, some questions are not okay. Now, most importantly, this whole process needs to occur while the data owner is not even present, right? Meaning the data owner loads in private data, creates an account, and then goes away and has a coffee, right? Doesn't have to actively maintain and administrate and read people's code manually and do all this sort of extra work and labor that's typically involved with adjudicating how people use private data, right? And this is really important to it for a lot of reasons, not the least of which is scale. But let's continue to fall and see what happens. So now the server is up, it's got this user, and now the user logs in to the domain server, using that username and password that was specified before, and then remotely this data scientist can generate answers to the allowed set of questions. Right? As long as the question the data scientist is bringing is inside of the subset of approved questions, right, by the data owner, then they can generate those answers automatically. And this is where all the privacy-enhancing technologies bits actually happens, right? This is the secure enclaves and functional encryption and federated learning and differential privacy and all this kind of stuff is in this process by which a data scientist can answer a specific set of questions and be limited in some degree to which what types of questions they're able to answer, right? And finally, and most importantly, they can download those answers automatically, right? Automatically, without having to, wait for the data owner to manually check off, right? Now notice what's missing from this process, bespoke data partnerships, meetings with lawyers, getting on the phone, background checks, any type of waiting or delay that is, the key activities that cause a data partnership, with a hospital to take 6 to 9 months, as opposed to it being a sub-second API call, right? And the bottom line here is that answering questions using an organization's domain server should be as easy as going to that organization's public website, right? So if those are the cars of pets, like this idea of domain servers, right? That's like what one organization can use to sort of do this. What are the roads of pets? What are the things that cars use to sort of actually get things done in the real world? And the roads of pets we just refer to as network servers or network nodes. And what these network servers do is they provide a variety of different services that are essential for the network to kind of run well, right? So one of those things is simply search and discovery. So, if I'm a data scientist and I need to find data somewhere out in the world, or if I'm a domain server and I need to be registered somewhere so that people can find me and find my data, right? That's what a network server is about. It's sort of like any search engine that you might be familiar with now. Second, we might have a legal consortia. So if you today, if you wanted to do federated learning across 1,000 different hospitals, you would need to go to every single hospital and redo your IRB authority or IRB board presentation over and over and over and over and over again for this kind of redundant check and redundant evaluation of the ethical compliance of your particular project. But data consortia as a legal tool have the ability to make this process a bit more efficient. So you can imagine that things like search and discovery and legal consortia or hosting secure VPNs, like sort of bubbles of trust, are all things that network servers can provide to help make the process by which a data scientist can work with data across many different institutions much more fluid and much sort of easier to do, right? So let's just take a quick look at what this might look like. So a data scientist has a science project, they submit it to the network server, there's some level of review that happens at the network server. The network server forwards that to the subset of domains that are relevant for that project. Some of the domains approve the project, some of the domains don't approve the project, and this might happen via automatic approval because of some rules-based system, or there might be some manual checking, or there's lots of flexibility in how this process can work. And then here's where privacy-enhanced technologies come in to facilitate the data scientist being able to perform remote data science against whichever domain server is opted in to participate in the project. right? And the broader story here is the idea that, in the same way that institutions around the world host, web servers with the data that they just want to make public to the world, they'll also be able to host domain servers with data that they don't want to make public to the world, but they want to facilitate people being able to answer specific kinds of questions, and they want their data to be able to help empower those types of questions to be answered, right? And so the idea is that in the same way that the internet is connected all of us together for this sort of public information, that this style of infrastructure will be appropriate to be able to connect us together for our non-public information. This doesn't necessarily mean it's always private data in the sort of sense of like data about people, but really any data that's just too valuable to just put on the open internet, right? So if before, when you wanted to do a data science project, you would go around and say, hey, can I have a copy of the data? Can I have a copy of the data? Can I have a copy of the data? And a bunch of places would be like, I don't know if I want to give you a copy of the data for a huge variety of reasons. Now the person simply logs in to a global network of data providers, submits their project, and is able to remotely sort of download the answer to their question without being able to download the data that drove the answer to that question, right? And importantly, this means that each of these institutions only has to decide whether they want to help you answer that question, as opposed to them having to decide whether they want to give you a copy of the data. It's a very, very different type of decision, right? So, how are we making concrete progress towards this technical vision? Well, let's take a little bit closer look at the text. So today I'm going to be talking to you about a library called PySift, right? And you can check this out online if you like. Now, the first tool that I want to talk to you about in PySift is called remote execution. Let's take a closer look. So let's say that I have, PySift imported into a Jupyter notebook, right? And if you're familiar with most statistical tools, you'll be familiar with the core data structure that they all use, right? Which is an array, right? Or a matrix or a tensor, right? These are different kind of words referring to the same idea, as sort of a nested list of numbers. And whether you're using Excel or R or NumPy or PyTorch or TensorFlow, they all kind of have this same core data structure. Privacy Answer Technologies introduce a new core primitive, a second core primitive, which is this idea of a worker, right? A specific party that is holding some data that I am going to remotely do analysis on, right? So in here we have an example here. We have this variable hospital data center on the left, and that variable is pointing to an actual computer in an actual hospital somewhere else, right? So if I take this, if I have a list of numbers 1, 3, 4, 5, I can send that list of numbers into the hospital, and what gets returned to me is a pointer to that list of numbers, right? And so this pointer X, has an API that looks and feels like the data is on my own machine. So if I go Y equals X plus X, it sends a little message into the hospital. It finds this tensor, this 1, 3, 4, 5, and adds it to itself. And what I get returned back to me is a pointer to that new result, right? So I can chain these things together and do remote analysis, sort of as if I was actually doing analysis on my own computer, right? And if I want to download the results of this analysis, I have this special method called .get, which reaches in and pulls the data out and lets me look at it, right? So why do we like this? Well, first, the data can remain on the remote machine. That's great. But how do we actually do good data science if we can't see the data ourselves? Well, let's talk about this second tool, search and example data. So let's say I have instead of just one worker at one hospital, I've got a connection to a network of workers at many different hospitals, right? So I search across this network. Hey, I'm looking for diabetes data. Is there any diabetes data in this network? Oh, look, we found some. Oh, fantastic, right? So now I have a pointer to this diabetes data set, right? And I can see the description and some public metadata. I can see how it was collected, what the different columns are about. I can look at different samples of this data, whether those were, hand generated or generated from a GAN, or perhaps they were just, sliced off and approved by the IRB board to be displayed in this manner. And the point I want to make with this is that, we already have a large set of tools for being able to work with data that's too big for us to see ourselves, right? And so it turns out that a lot of those features that we use for data that's simply too big for us to read all of ourselves translates over relatively nicely to data that's simply too private for us to see ourselves. Okay, now, if before we had this method called .get, right? I had this pointer to X and I was able to just pull it out. What keeps us from being able to just download remote data sets this way? Well, for that I want to talk about a tool called differential privacy. So on the left side here, I've got a database, right? We've got Bob, Bill, Sue, John, and zeros and ones, and those zeros and ones roughly correspond to true, false, right? So the goal of differential privacy is to ensure that the output of statistical analysis does not compromise privacy, okay? So if I'm querying a database, right, the sort of intuitive definition of perfect privacy is one where the output of my query is exactly identical between this full database and the same database with one row removed or replaced. Or put another way, if I, query this database and I get an answer, and then I remove Bob's data from this database, and then I query the database again, well, if the output of this query doesn't change, then it wasn't really dependent on Bob's information, right? It doesn't really matter if Bob's there or Bob's not. I'm clearly not leaking any information about Bob because it's not changing the answer, right? And so the interesting thing is, if I can show this for everyone, then I'm perfectly protecting the privacy of all the individuals in the database because I'm not leaking individual information about any one of those particular individuals, right? However, there's not very many queries that are like that, and so we have a slightly different approach to sort of pursuing this definition of perfect privacy. So let's say I wanted to survey a group of you, right? And I wanted to ask you a true-false question where I thought you might lie to me. Like maybe I'm trying to figure out, what's the percentage of the time people, what's the probability, or the number of people here who have COVID, like right now. And so I sit you down and I give you a coin, like a quarter, like the one we see here, and I say, flip this coin twice somewhere that I cannot see. Flip this coin twice somewhere that I cannot see. And if the first coin flip is heads, I want you to answer honestly. But if the first coin flip is a tails, I want you to answer true or false according to the second coin flip. So what that means is that roughly half the time you're going to answer honestly, and half the time you're going to answer yes or no based on a perfect 50-50 coin flip. Or put another way, what it means is that roughly half of you, half of the group, will be honest, and half of you will answer according to a 50-50 coin flip, right? Or put another way, it means that my resulting statistic, right, whatever the true statistic is, let's say 60% of you have COVID. There's a lot of sick people. That 60% of you having COVID is going to be averaged with a 50-50 coin flip before that information is sent to me. So if I receive, the results of my survey, and it says, 55% of people have COVID, I will know the true center of the distribution was actually 60% because it had been averaged with a coin flip. And the amazing part about differential privacy is my ability to recover that true center of the distribution, that true statistic, right? Despite the fact that I don't know which one of you was lying or telling the truth, right? So even though I'm able to still figure out that 60% of people had COVID, any individual person might have flipped a heads or a tails in their answer. So now let's come back to the scenario we had a minute ago, where we had a pointer to a data set that was inside of a hospital, data set about diabetes. And I call .get, and it tries to download the data. It says, whoa, 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 whoa. You just requested a data point which is private, or which depends on data which is private. You can only query private data if noise is added. Use .get epsilon to add the appropriate amount of noise. Now this right here, epsilon, is a measure of what's called privacy budget. Now if you go back to our coin flipping example, you remember the first coin flip determined whether or not you were going to be honest or lie, right? And so you can imagine that I can actually bias that coin flip to cause more people to be honest or more people to lie. Now why does that matter? Well, if I biased it so that everyone was honest, then no one was protected anymore, right? Because everyone was honest. I would be able to reverse engineer. I wouldn't have to reverse engineer. Everyone's telling me exactly whether they have COVID or not. If I were to bias the coin flip the other way, then eventually, everyone gets more and more protection. They're less and less and less and less likely to have COVID, even if they say yes, because everyone's answering according to the second coin flip. And so what this roughly corresponds to is a measure of risk. And in the differential privacy literature, this corresponds to something called a privacy budget. A privacy budget, right? And what a privacy budget is it is a limit on the amount of unique statistical information that someone can learn about a specific person in the data set. So if a data owner loads in a data set and then of medical records or something, and then gives a privacy budget to me, the data scientist, then that means that I can download all of my statistical results, right? All my analysis, my machine learning models, whatever the case might be, as long as the sum total of all of my downloads is underneath a certain privacy budget. And that privacy budget is measured in increments called epsilon. Epsilon, right? So here I spent 0.1 epsilon, which means that it took each one of these values in the data set and added noise to it, just like we added noise to the coin flips before people responded to say whether or not they had or didn't have COVID. It's the same idea of kind of plausible deniability being given in the form of noise. And what I did in this query is I said, hey, add enough noise so that I'm only spending 0.1 epsilon. Okay? So we've got a wide variety of tools now, right? Data remains in the remote machine because we've got remote execution. We've got search and sample data, which we can use to do feature engineer and do all sorts of interesting things. With differential privacy, we have formal, rigorous privacy budgeting, which is super cool. But we have these problems, right? While the data is safe, the model is actually put at risk. And what if we need to do a join on data across multiple different data owners? Well, for this, I want to talk about a tool called secure multi-party computation. Secure multi-party computation. And the textbook definition of secure multi-party computation looks something like this. Like, multiple people can combine their private inputs to compute a function without revealing their inputs to each other. But the implication of this is that multiple people can share ownership of a number. Share ownership of a number. Okay? So let's say I have the number 5, and I split it into 2 shares, a 2 and a 3. And I have 2 friends, Marianne and Bobby, and I give them these 2 shares, and I disappear, right? And 2 plus 3 equals 5, right? That's the relationship between these 3 variables. And here's the extraordinary thing. Neither Marianne nor Bobby have any information over what number is sort of stored in between them, right? Because, for all Marianne knows, Bobby's number could have been negative 2,564,455, or it could be positive 2,565,465, right? They have no information on what number is the sum total of all the shares because they don't have access to all the shares. And so as a result, we say that this number is encrypted between Marianne and Bobby, right? Neither of them know the hidden value. But more importantly, it also has shared governance, right? Meaning the number can only be decrypted and used if everyone agrees, if all of the shareholders of this number agree. But perhaps the most extraordinary aspect of secure multi-party computation is that while this number is encrypted between them, they can perform arithmetic. So let's say Marianne multiplies her share times 2, which equals a 4, and Bobby multiplies his share times 2, which equals a 6, and now our 2 and 3 have turned into a 4 and 6, which is an encrypted number 10. So even though neither Marianne nor Bobby know what number is encrypted between them, they're able to compute over it. Now, if we take a step back, remember that statistical models and data sets are just large collections of numbers, which we can individually encrypt. Now, let's put all these tools together and see them end to end, so we can sort of see how they all sort of fit together. So I import SIFT, and what's the first thing I do? The first thing I do is I look for networks. Remember I was talking about networks a little while ago? Networks are these big registries of domains that also host VPNs and can provide some other services. But the first thing I want to do when I want to find a data set is to look for some networks. I see I've got some networks here. Now the project we're going to do here is actually from the United Nations Privacy and Technology Lab, and the the use case is the trade use case that I mentioned at the beginning of this talk, where we had trade from the United States and trade from Canada, and we wanted to see if these statistics actually matched up. So let's do that, okay? So I'm going to select a network, right? And I'm going to see a list of domains, and see, I've got a variety of different domains. Oh, look, Canada and the United States of America here. Okay, so two different servers. One of those servers is in Canada, one of those servers is in the USA. So as a data scientist, what do? I'm the data scientist, so I'm going to log in using my data science account, right? sheldon@caltech.edu, right? And what logging in means is that I have this variable on the left here, CA, for my pointer to the computer that's in Canada, and USA for the pointer to the computer that's in the United States, that's holding this trade statistics, these trade numbers. So I connect to them. All right, awesome. I'm connected to Canada, I'm connected to the United States. Fantastic. Now, the first thing that I do once I'm connected is see how much privacy budget I have. Looks like I've got loads of privacy budget, 200 epsilon piece. Fantastic. Now, the next thing I do is need to find what data sets. So in Canada, looks like there's a trade data set with the United States measuring the amount of dairy produce, right? Dairy produce, birds' eggs, natural honey, and edible products of animal origin. So there you go. And it looks like inside this data set, it's got 3 assets: imports, exports, and re-exports. Okay, pretty cool. And then in the United States server, it looks like it's got trade flows with Canada. And it also has dairy produce, birds, eggs, natural honey, edible products of animal origin, which is like an official description. It's published by official statistics community. Okay, so now we've got a data set in the United States about its flows with Canada. We've got a data set in Canada about its flows with the United States. We're good to go. So what have we done here? We've selected the exports, right? Recorded by USA. We've selected the imports recorded by Canada. And now what we have are pointers to those 2 different tensors, those 2 different numbers actually in this case. So USA exports to Canada is how much the United States thinks that it's exporting to Canada. And Canada imports from USA is how much Canada thinks they're importing from the United States. Now, this cell right here is really special because this should be impossible, right? Because don't forget, USA exports to Canada is pointing to a number on an actual computer in the United States. Canada imports from USA is pointing to a number on an actual computer in Canada. It's in a different country. And yet we have asked for those 2 numbers to be subtracted so that we can see how much they differ. And so the surprising thing here is that this executes, right? Now, let's talk about how it executes. First thing that happens is it goes, wait a minute. These are pointers on 2 different computers. We can't do arithmetic on pointers from 2 different computers because they can't interact with each other, right? So what it does instead is it goes to the United States and it takes its number and it splits it into 2 shares, right? And sends one of those shares to Canada. Then it goes to the Canada server and finds that number and splits it into 2 shares and sends one of those shares to the United States. All of a sudden, USA exports to Canada and Canada imports from USA have the same shareholders. Because they have the same shareholders, you can now use them together for arithmetic. And so what is the result of that arithmetic? A new shared tensor. And that tensor has the same shareholders as the inputs that created it, which means I can only download or decrypt or use this result if Canada and the United States both agree to let me. It is under joint ownership, joint control by both of those shareholders. And how do I convince them to release it to me? I spend part of my privacy budget in Canada and the United States. If you remember when I set this up, I had privacy budget in both places. How do I do that? I add noise, of course, but I ask for this publish event. Now it gives me a new variable that has noise on it that I can download. I see that there's a $1.6 million discrepancy between these 2 things being recorded. And of course, I've spent a bunch of my privacy budget in the process, right? So now I hope you see sort of the vision of what this interface is really all about, right? The idea that a data scientist can sit at the center of a web of different data servers, right, in different countries, run by different organizations. And from the data scientist's perspective, it kind of feels like all the data is actually already on their own machine, right? They can do, arithmetic and complex analysis and work with tensors as if those tensors were on their own computer. And all the, kind of governance sort of handled behind the scenes. All the privacy-enhanced technologies are kind of hidden under the hood of the car, right? If that makes sense. But inversely, the data owners, they set their privacy budget and they left, right? They set their privacy budget and that was the mathematically rigorous way in which they were saying, hey, you're allowed to answer questions of this type, but not questions of another type, right? And so what I hope you'll see is that it's a really exciting time for privacy-enhanced technologies in the sense that and so the picture I wanted to finish here is this picture of the early internet, right? This idea that small collections of institutions are starting to network their information together, and it's the beginning of something kind of bright and new, and that these technologies really do offer the promise to unlock orders of magnitude more information in every scientific field, which is an incredibly exciting development. Thank you so much. Hope you enjoyed this presentation, and chat to you soon.